So attendees of the class did standard academic didactic studying homeworks, but in addition, they were so enthusiastic that they, by their free will, they volunteered to do mini research projects. Okay, so the materials in class were used to do projects, and the arrangements of the order in the project based on the following thoughts. The equations of and ideas of physical chemistry are applied to different, more or less practical problems, and each of the practical problems have either 1 or 0 or 2 of the following 3 things: electronic degrees of freedom, nuclear degrees of freedom, or electromagnetic field. And one can categorize different talks, and we are trying to go from electronic to vibrational to electromagnetic, but things maybe not in a straight order. It is expected that the talk goes for 5 minutes, and then there is unlimited up to 10 minutes time for questions. So if there are questions, they are very welcome from each other and from visitors, and we should be finished by about 12:30. So you can, if you come to present on the stage, you see here on the desktop of this computer, there are all of your presentations. They are labeled by numbers and by the names of the presenters. So just double click it to pop up and put it into the presentation mode. So let me invite to the stage the first speaker, Sam Stevens.
It is. Oh, wow. Shocking. Okay. All right. So my project was on the interaction of electrons in single-walled carbon nanotubes with sp3 defects described by the Slater determinant. I guess a little bit of background on what you'll be seeing, and I can show it in a photo, is the defect that was used was aniline at 5 different spaces. The 2 we're going to be looking at is a single bond length away, and then at 2.5 nanometers away. So when looking at the first figure here, some important notes to make is that this blue line, I guess, I don't know if on the Zoom, if they can see what I'm pointing at with the laser pointer, but for the bottom figure, the blue kind of like, the blue line is the potential as you go across the carbon nanotube. And if you notice, as you get closer to your defects, your potential increases. You also can see like an orange and a yellow line right here. This is going to be the eigen function offset by the eigenenergies. This distance right here also indicates that there is some optical activity within the carbon nanotube with these defects. We can take a look at the second figure here and see that due to, like, as the distance increases, that separation outside, like away from your like defect itself, has very minimal separation. Another thing that we can note as well is as you, okay, I think the top of the figure is kind of cut off, but you have 2 kind of like different colors. They're probably not very easy to see on Zoom or maybe at a distance, but as you like go up on your potential towards the positive, those are just higher eigenstates. I think that's everything on that. And then I guess when you just compare, yeah, like right here, like as you get closer to 0, your eigenstates get higher and higher, and you can kind of see it really well at the top 2 here, as those are just 2 higher eigenstates. Do you want me to, I think you have access to that. And continuing on. So I guess kind of what I was just talking about, you can see the higher eigenstates, the eigenfunction, which is offset by your eigenenergy and your potentials, and then just comparing our single bond length away in 2.5 nanometers. You can see that at the 2.5 nanometers, your potential is, I'll call it prettier, and it's kind of easier to see. It's a lot more like congested, and like you have one single peak at each of the carbon or the defects for your 2.5 nanometers, while you have kind of like a set of 4 at the one bond length. So now getting into the math and I guess more the work of what I was trying to get at. So when looking at the single bond length away, we have our eigenstates of 1 and 2. We have what is known as the Hartree product, which is, oh, maybe I didn't. So the Hartree product is basically just when you have your eigenstate or the wave, I believe it's the wave function of your eigenstate 1 times the wave function of your eigenstate 2, subtracted from when you flip your eigenstate, or your eigenstate 2 and 1, or particle 1 and 2, being denoted by x1 and x2. When those eigenstates get flipped, the difference comes out to be the Slater determinant, which is shown by this equation below the third figure on the right. And then just same thing here, except it's at the 2.5 nanometers away. I think, oh my God, nice little thing about this figure. I think this one just shows it a little better of how, like, you have, this is 0 is the yellow. I don't know why it's green over here, but yellow is 0, and then when you subtract it, this becomes positive because the blue is negative within these figures. This, I think, shows it a little more, like, shows it, but I think that it doesn't show it as well as this figure. So getting into, I guess, the results based on what our Slater determinant shows is as the defect distance increases, our Coulomb potential, which is shown by our equation right below our the graph right here. These are the same, just one I think visualizes it a bit better. It uses our Slater determinant and Slater determinant, and then did I not put that equation on there? Maybe I didn't. But yeah, so Slater determinant, and I believe that's the Hartree product. And then, as we can see, as the distance increases, our potential decreases, and between the first 2 defects, there's a pretty significant potential decrease compared to as the defect distance increases. And then, I guess, leading into my last figure, which is changing the eigenstate value to 1 and 4 when comparing. This is the just Slater determinant. You can see that it's a lot. Oh, I should say this is also at the 2.5 nanometer distance. So compared to the 2.5 right here, there's a lot more going on in the figure. And what I hypothesize from this is that as you have like these alternating positive negative functions along the x and the y, I believe that is we have like the 4th eigenstate compared, like the potential difference between eigenstate 4 and 1. And then as you like kind of go farther down the x-axis, I believe this is like 3 and 1 and then 2 and 1. That's what I've hypothesized on it. I kind of ran it out of just to see kind of how the Slater determinant would, and like the figure and potentials would look different. This is the potential energy that would come out of it, which is the number that you would have here with your Coulomb potential. And you can see that it increased as your eigenvalue is different. And that's it.
Okay, there are questions from the audience in class. Yes.
When you change your eigenstates from 1 to 2 to 1 to 4, was that just sort of arbitrarily chosen for, or was there a specific reason you chose that?
It was just kind of to have a significant like eigenstate difference. Like I could have done 1 and 3, but just kind of doubling our higher eigenvalue just to see. Yes, Dr. Newman.
Could you explain a little bit what is Slater determinant and why you need it?
So the Slater determinant, correct me if I'm wrong, because I know what it mathematically does. In terms of it compares. Oh my God! Can I please get the So it compares the wave function of two particles. Yeah, I should know this a lot better than I feel like I do. So it compares the wave functions of two particles that aren't discernible. So what I guess I mean by that is the reason we use the Slater determinant, and I guess it also, the Slater determinant is the anti-symmetry of the comparison of two wave functions, which is basically if we were not to do the Slater determinant when comparing two particles, our like potential would go to a positive infinity, and you can't really have that. So when you do the anti-symmetry with the Slater determinant, it gives you a finite number, which allows us to get the potential interaction between the two particles. Is that a good explanation? I think that's my understanding of like the Slater determinant.
I asked a question. Okay,
Are you using periodic boundary condition?
Can you repeat that one more time? I couldn't really hear you.
Periodic boundary condition in your model?
Yes. Yes. Yeah. The boundary is, I believe, 100
just tell,
atomic units.
were you doing the whole work or you imported something from helpers?
Oh, I got my potential function, I believe, from Dr. Khan. So
your potential energy increases with distance, right?
yes.
Yeah, but I have seen in several literature the different when they come closer, they are more stable.
They're more destable.
Yes.
It's
It wants to be clustered at the nearest distance. Is it true?
So the findings that I had were that as your distance increased, the potential energy would increase. So yes, yeah, that would yes. I'm trying to think here logically. If the potential increases,
But let me comment. So, Dinesh, just rules of the game. Please design your questions as an exam question for third year undergraduate. It's not a research meeting. It is evaluation of their skills at the level of third year of undergraduate school. Okay, but please, questions are very welcome. Let me help to Sam to answer the question.
appreciate it.
The question from Dr. Tappe deals with overall total energy, and Sam is evaluating only Coulomb repulsion, which is predominantly positive. Make sense? Okay. So the next speaker of the day is Frederick Lanier, and he is going to report results of the.
It's too loud. Oh my god, it's pretty loud.
Modeling Polaron formation in the conjugated polymers or oligomers conjugated polymers. And in his work, there will be simultaneous cooperation between electronic and nuclear degrees of freedom. Okay, what is yours?
All right, so we're talking about polarons in conjugated polymers, how the dielectric constant of the medium which that polymer is in affects the localization of that polaron and its size. So polarons are formed when, or they can be formed in a lot of different compounds, but in a polymer, like a conjugated polymer, when you inject an electron into it, the forces between the electron and the carbon atoms, which are acting as ions, will cause the electron to kind of get trapped in a certain spot in that polymer. And it begins to act as its own like unique particle with an increased effective mass. And that's a polaron. So large and small polarons behave a little differently, and they could possibly affect the conductivity and other properties of a material like a conjugated polymer. There isn't really, there's a lot of research still being done on them. As far as I know, they're kind of like theoretical, but it has been found that, you know, polaronic interactions can affect the conductivity of a material, such as a conjugated polymer. So, like I said before, we're talking about dielectric constant. So this will probably affect the size of the polaron. It'll affect how well it localizes, how much it's trapped in that conjugated polymer, because dielectric constant is essentially a measure of how polar that solvent is. Higher dielectric constants will reduce the force between charged particles. So it makes sense if we put this polymer into a solvent with a really high dielectric constant, it will decrease the force between the injected electron and the carbon ions around it, creating a less localized polaron and perhaps a larger polaron. So for my methods, we start off with an initial wave function, which follows this time-independent Schrodinger equation. It updates its probability density, potential, and position. And if the change in energy of this wave packet is lower than the tolerance limit that's been set in the program, it will plot it as data, pretty much. So this is the time-independent Schrodinger equation for the ground state wave function of the electron. The equation of motion for the position of each ion in that polymer. These equations are Hooke's law for the force between the carbon ions. So the force between a certain carbon ion and the ion next to it on one side and the ion next to it on the other side for these two different equations. And then this describes the Coulombic attraction of the ion to the injected electron in its ground state. So we have our dielectric constant here that we put in, and that's what's going to change the shape of our wave packet at the end of the simulation. Also forgot to mention, in this specific model, we're using cis polyacetylene, and kind of arbitrarily I set in the code for there to be 16 carbon atoms. So here is kind of a movie of how this is like the initial wave packet of the injected electron. The red line kind of represents just like the theoretical overall shape of that initial wave packet. And then once it's injected, I'm going to speed it up because it's pretty slow. Once it's injected, it will slowly, I mean, it's kind of hard to see like as it moves, but it will kind of localize to a more narrow wave. God, come on.
Try to loop it so that it doesn't stop when you.
Can I do that?
Yes.
I mean, I can explain well enough here. So like before, okay. So this area here represents the potential well that the polaron sits in the polymer. So you see originally all these levels, these green peaks represent the potential, the attraction between the electron and each carbon ion. So as you can see here in the middle, these start to change. It becomes a potential well, and the wave packet also narrows and localizes to this area. So this is where the polaron would be forming in the polymer. Oh, wait. Okay. Oh man. Well, now it's. Oh, there we go. Okay, okay. So this is a kind of better way of visualizing it from start to finish. So based on these different dielectric constants, the video I just showed you was I just picked a random one pretty much. But that was in pentane, which has a pretty low dielectric constant. It's pretty nonpolar. A vacuum, honestly, well, obviously there's no solvent, so it creates the most localized polaron, the smallest polaron. And as we start to increase the dielectric constant to 1.84 for pentane, the final wave packet, it is localized compared to like its initial width, but it is still slightly less localized than it would be in a vacuum. And following that pattern with ether, it's a lot less localized, pretty wide here. Still more narrow than it started, but you can see the significant difference between dielectric constants, how if you increase it, the wave packet tends to be wider at the end of the simulation. So as you'd probably noticed on this slide as well, with increased dielectric constant, the wave packet tends to move to one end of the polymer. To be perfectly honest, I'm not sure if this motion is like exactly representative of what really happens, but it is what happened in the code, and it makes a little sense because larger polarons that would be less localized, it would be wider. They tend to move in. They tend to move more. A smaller polaron is more localized. It's more trapped, but a larger polaron moves in sort of like a band, sort of a wave motion is what I've read in papers at least. So here we see with a really, really big dielectric constant in a polar solvent, methanol, dielectric constant is 32.7 compared to 1.8, 4.3. It moves to like the very end of the polymer, and it begins to narrow slightly. I think of it kind of, the wave packet is getting like squished up against the end of this polymer. But then at really high dielectric constants, I saw between like 8 and 19, which I know is a really big range, but somewhere in between there, it begins to, it's constant. So a possible conclusion would be that polarons, might not form in solvents with high dielectric constants because they're not localized enough. And here we see this pattern kind of graphed out better. Here in the vacuum, the width of the wave packet's super narrow. As it increases, it gets a lot wider. And then around here, coincidentally, is where we switch from nonpolar to polar solvents. It begins to narrow and kind of drop out of this pattern. Yeah, I guess I talked about that. Lower dielectric constants cause smaller, more localized polarons. In solvents with high dielectric constants, a polaron might not even form, but I can't say for certain. But for sure, more work needs to be done, like possibly with this simulation to better explain it.
Okay. So, questions in the audience?
Yes. So I guess the first question is, how did you propagate your wave function?
Well, like I said, I'm not entirely sure why this moves the way it does to the end. I believe it has to do with this Newtonian equation of motion. Oh wait, actually, no, that's not true.
Let me assist and
Yeah.
help. I will not answer for him. I'll just help. Bring back the questions, please. And I will reformulate the question. Do you propagate wave, electronic wave function? Or you do something different?
I mean, to be honest, I thought that if it was well, I mean, actually, no. I mean, since it's time independent, it relies mostly on like the energy state that wave packet has, that electron is in. So then it updates like based on, you know, one energy state and then the next and then the next. It doesn't really, this specifically doesn't depend on time.
Okay. And in this, in the first equation, which number I do you use in your model? Which order?
Over here? When I believe, can't really remember, when I was equal to 1. Yeah, oh yeah. So,
Does that answer your question?
okay.
So in your first equation, then how did you calculate the potential?
The potential, I believe, is I don't know if this variable gets changed from one equation to the other. I couldn't really say off the top of my head, to be honest.
But let's try to constructively think.
But I would think that it has to do, you know, with the Hooke's law and the Coulombic attraction. That.
Let's show you a movie.
Okay.
Okay. And,
yeah.
Where do these green lines have their meaning?
Well, at the position of each carbon ion. They would. Their minima is up here. Yeah.
Does the green line relates to the V of x?
To what?
V of x that Dr. Khan is asking you.
Yeah. This represents the potential that is.
So
the potential that goes into the Schrodinger equation. It's based off of the location of each ion and the charge of each ion, which is set kind of like arbitrarily. Most of the units are like, well, in the simulation, I mean, like it's all pretty relative.
Dr. Khan, does that answer your question?
Okay.
Yeah. Thank you, Frank, for being brief.
Okay.
It was not easy, but there could be more questions. Anyone wants to please, Fred, please.
Yes. For getting which of wave packet positive and negative polarity both, or?
No, I kind of just ran this. Wait, can you repeat it again? I'm not sure.
How does your wave packet vary with positive or negative polarity?
Let me translate.
Yeah.
Do you inject electron or you remove electron?
We are putting an electron into it, so it would be a negative polaron.
You didn't.
No, we just it's pretty it's a pretty narrow yeah.
Dr. Staffan, you have high expectations for the 3 big projects.
So
I just asked.
Sam.
Yes, Sam.
Smaller,
oh well, I actually. I wasn't going to mention it, but I did a little bit. If a smaller polaron is more confined, it's more trapped to, it's more localized on one ion in the polymer. If it does move, I read it's more of like a hopping mechanism that is. I don't know exactly. I can't remember how it's catalyzed, but like there has to be something done to the polymer usually for a small polaron to like hop from one ion to the next. But a larger polaron, which is more delocalized, I read tends to kind of move more on its own through the polymer in like a wave fashion.
So let's double check.
David? David's got a question.
Go ahead.
So you talk about different solvents. How do you factor the solvents into your work?
Well, I'm sure there's other factors that could play into how the solvent affects the formation of polaron, but I kind of wanted to just focus on dielectric constant. So I just found a big list of all like the common solvents, or not all of them, but like a lot of common solvents. And I just put the dielectric constants into here, into the equation for the Coulombic attraction of the ion to the electron. So if there's a larger dielectric constant here, it'll be less force between the two.
So my presentation is electrons that are excited by an electric field in cyclic voltammetry. Just the middle button. Oh. So cyclic voltammetry, just as a background, is a category of electrochemistry. Is this close enough? No. Sorry, I don't think this is close enough. An electric field is applied using something called a potentiostat, and it increases the energy of the electrons in a molecule until electron transfer becomes favorable. So until the electron is capable of moving from a molecule to an electrode. So you can do this on species such as like molecules and polymers. The flow of electrons is then related to different chemical changes, such as the oxidation or reduction of the species. So this is the equation in MATLAB that was being manipulated to provide the results. So the E naught value is the slope of the electric field being applied, which is what increases the energy of the electrons. And then the variable VV, I believe, is the initial speed of the electron, which is V subtest times 0, because the initial speed of the electron would be 0 before any energy, before any electric field is applied to it. So in the video, you would see this red function here moving as like a wave function from this area of peaks in the graph to this area of peaks. The first one represents the molecule that it's moving from, and then the second one represents the electrode that it's moving to. And so in this scenario, the E naught value would be 0.08 volts, creating a big enough slope in the graph. And then in the next one, you'll see one that's a little bit tighter of a picture, so it looks a little better, but creating a large enough of a slope, meaning that there is enough energy in the electron for it to be favorable for it to move from the molecule to the electrode. Meaning that a reduction or oxidation is, well, in this case, meaning a reduction did occur. So here's the video that was supposed to be in the presentation. And so once it hits the side, so the barriers of the box, it gets really gross, and that's kind of where data collection would stop. Here's the next one. So this is where the applied electric field, so the value of E naught would be 0.001 volts, and anything like 0.001 or less is going to give you this really flat slope, where it's not going to have enough energy to allow the electron to move from the molecule to the electrode, which means that no reaction will occur and no data will be able to be collected. So here you'll see how it moves only over the area that represents the molecule. Then some conclusions to kind of take away from this is that electron transfer can be modeled by a MATLAB code. The transfer can be seen by the function representing the electron, which was that red wave function, moving from the molecule to the electrode, which was represented by the upside down peaks of the bright green function. And then when the applied electric field is great enough, there's a steep enough slope, meaning there's enough applied electric field to increase the energy of the electron for electron transfer to be favorable, meaning a reaction will occur. And that's all.
Okay, question stands for the perfect timing of 5 minutes. So any questions to the speaker?
The question actually.
Okay.
Sorry, you know.
Please, like everyone is very welcome to ask questions, just to have a little more order in case there are several. Raise your hand. But go ahead.
Right. Does this apply for almost any environment and one molecule?
I believe so. Yeah, as long as you have the right conditions. With a polymer and or molecule that is that can be dissolved in a solvent, and the proper electrolyte to carry a charge through the solvent, I believe that yes, it would work. Sam?
Did you use a specific molecule as an electrode, or is it just like a generalized like?
I'm honestly not totally sure. I believe it's just a generalized kind of description of what's happening and how it would happen. As far as I'm aware. Right.
Did you find like an exact point where, like at least for your model, where it would transfer over?
Yeah, actually, I think the 0.08 was around where it looked the best. Because anything less than that, it was really slow. And anything more than that, it was so steep that it got super messy super fast. So yeah.
Another question from Sam.
I was gonna say, do you think that there's a way within the MATLAB code that you can like so that you can get like that data collection before it gets messy to like end it by the time that it reaches the end of your like sequencing?
I mean, probably you can probably cut it off somewhere within the code at a certain time so that it doesn't run any farther than that. But I could not figure out a way to cut it short with the code that we were provided. Okay.
On your figures, you talk about the green and the red line, but there's a third yellow line. What does the yellow line represent?
You're talking about this one here?
Yeah, those figures.
This one? I'm not entirely sure. I was told to focus on the red function, that one is the one that represents the electrons, but I'm not entirely sure what that one represents.
Just try. Is it a different way to model the same thing?
Mm-hmm.
It was a part of previous presentation like a month ago when there were like method 1, method 2, method 3.
Is that the one that represents just the wave packet, or?
So different way to represent momentum operator. Just say yes.
Yes.
Okay. Yeah, Dr. Khan.
Please put your equation and then explain each term. Suppose we have not read the one.
So this one, I believe, is the initial speed of the electron.
Think again and repeat.
Is it the initial energy of the electron?
Go to your movie or diagram. I will cut this part from the recordings.
Okay.
So make connection between your potential and this green line and try to start over.
And what green line? The bright green line?
Yeah.
This one?
Yeah. Like explain what is this green line and then make correspondence to the equation.
Is it just the initial value of the electric field, or
equation? So your E naught is an electric field.
yeah?
X is just distance or something corresponding to the dipole. And what is PV? Because this function up to the minus is just a linear slope.
Right.
It doesn't have any features for the atoms.
Well, that would be, I guess, the starting position of something, because just in.
This should be a function of X.
Okay.
Explain by words what the green function. How does it look like without showing it? Just show by fingers. Explain how the potential looks like.
It's just something with a negative slope.
What else in addition to negative slope?
With like peaks upside.
Okay, so what are those peaks?
The, I guess, location of the molecule and location of the electrode.
Okay. And now check, maybe Dr. Han will accept this as an answer or request a little more details.
Yeah, that's good enough.
It's good enough? Okay.
You see, I was very nervous. More questions to the speaker? Here or online? Yes, no? Okay, let's thank Elsa once again.
So today I'm going to be talking about, sounds really loud, about two-dimensional modeling of enzyme catalytic reactions. So the enzyme that I'm focusing on a bit more specifically is chloride dismutase, or CLD for short. And this is sort of a video that is generally describing what we're going to be focusing on here. So chloride dismutase is a heme-based protein, and it is responsible for converting. So CLD is responsible for converting nitric oxide with a hydroxide, and it produces nitrous acid. So throughout this study, I have been looking at two different interatomic distances. One is from the, is it going to loop now? Ah, nice. Okay. Oh boy. Okay. So two different interatomic distances. One is from the iron in the porphyrin center, which is labeled in that kind of brownish color, to the nitrogen of the nitric oxide, and also from the oxygen in the hydroxide to that same nitrogen. And part of why this study sort of generally is important is that nitric oxide can be toxic in biological systems. However, converting it to nitrous acid and then the conjugate base, which is nitrite, that is used later by hemoglobin, which sort of helps travel oxygen around the body. So this is sort of a closer up look at what the different distances that we're taking a look at. So X and Y labeled here. I had a MATLAB script that models the catalytic reaction, and I was able to not only follow the different distances and sort of how they changed throughout the reaction, but also take a look at the eigenstates that it produced and the energies sort of related to it. This is a energy corresponding to the eigenstates equation that I have here. So N and M are quantum numbers for both degrees of freedom, M and N, which is sort of X and Y. And then, so this is a figure that I took a look at also previous years. Braden took a look at this as well. So there's a couple different things going on in the picture. On the top, the x-axis is the distance between the iron and nitrogen, whereas the y-axis is the distance between oxygen and nitrogen. The dashed line here is the molecular dynamics trajectory. So this is according to classical theory. There are blue and yellow spatial regions. These are represents the potential. So yellow is the positive potential and blue is the negative potential. And then the solid line is a sort of quantum corrected version of the trajectory. So that is, it's not the same as the dashed line, but the dashed line is the classical theory, whereas the solid line is more quantum mechanics. Okay, so got a video here. So these are the eigenstates. Again, I have that equation listed. So a couple things to point out here. Oh. Okay, you don't want to work. There we go. So looking at the figure on the left, there are no degenerates. So there's no eigenstates that have the same corresponding energies to them. And as the values of n and m, or as the eigenstates increase, the energy also increases. Now it's not a perfect representation of the equation that I have above. That equation is just more of a starting point. Then the video that's playing, it goes up to 40. Those are the 40 different eigenstates that we chose. And this figure was created by taking a look at the energies and everything on the video on the right. So again, as the eigenstates increase, there's going to be more of those positive and negative spots, and those represent the eigenstates themselves. Yep, I just said that. And then this is a simulated run. So this is an interesting situation going on. The video itself is 5 minutes long. The code took 5 hours to run, so I can't play the whole video. That would be the entire presentation. But I'll give you kind of a rundown of what's going on here. So although the time is increasing pretty rapidly, it goes up to 10,000. So we're not making a whole lot of progress at the pace that it's at. But even at 2 times speed, it takes 3 minutes. So we still don't really have time for that. But as it progresses, a couple different things to point out. The rings are sort of the probability of the species to exist there. So the general progression is going to be from the top left over to sort of the lower right. So that represents it converting from the reactants over to the products. The longer that this goes, it's going to create a sort of blue dashed line that kind of represents the path or the trajectory that it is actually taking. So that's similar to the either dashed or solid lines that I showed a couple figures before. Then the video gets to a point where it starts to get a little bit wonky. There's a couple different potentials as to why the code may be kind of reacting strange. It's possible that the code just wasn't sort of able to handle as many time points as we were trying to kind of shove upon it, which is also part of why it probably took so long to run. And my computer almost exploded every time, but that's okay. Another thing is that we are trying to introduce classical and quantum mechanics. So it's possible that that was just sort of a bit of an overwhelming process for it as well. So I'll just kind of skip a little to the end, and you can see it just kind of gets uglier and uglier. So it starts to malfunction, but ideally it would have continued making those blue dashed lines that it starts here at the beginning. So general conclusions that I have is the code was overall successful to simulate the reaction in this conversion. The bond distances, again, between the iron of the porphyrin ring and the nitrogen, as well as the oxygen and the nitrogen, were able to be followed throughout this reaction. The eigenstates, again, were plotted with their corresponding energies, and there were no degenerates. And it roughly follows the equation in the sense that as the eigenstates increase, the energy increases. Acknowledgements. Special thanks to Dimitri for all his support, also to Braden and Sibel. They did a lot of preceding work related to this project. So this is kind of a continuation of that. And then my sources.
So any questions to the
Yes, Fred?
So the movement of your model in that long movie from like top right or top left to lower right, is modeling the probability of it turning from reactants to products.
Yes, essentially.
Turning from reactants to products.
Yeah, so if we go back 1,000 slides, That's sort of part of what's going on in that top image. So again, it has the dashed line, which my video roughly followed. And then also one thing to notice, oh, I didn't even point out the image on the bottom. Thanks, Fred. Now I can talk about it. So the image on the bottom is kind of a sideways, more 3D view of the image on the top. So again, the blue region does the laser work? This blue region here is negative, which is why it is negative here in this area. So there's less energy that's needed for any kind of species to exist there, which is also part of why it takes that path to convert, because it requires less energy rather than having to kind of climb out of this canyon. Yeah.
Well, it's kind of a follow-up. Okay, so at the end of your movie, where you have like a bunch of little, like, kind of like condensed areas. Like,
yeah.
Basically, there are more areas where you could easily be present.
So my understanding is the kind of circles that it made around, which I think is what you're talking about.
Yeah.
In this one.
Yeah,
like all the circles around it. It's kind of just saying generally that it's possible for the species to exist anywhere kind of in that region. So the farther out it gets, kind of the less likely it is to be there. Of course, the closer to the bullseye, I guess, the more likely it is that the species exists in that area. But we're not able to pinpoint it quite as accurately as that, I guess. So it's just sort of generally the region that it could be. I don't know if in the code they necessarily were all supposed to still be there, it's a little overwhelming of a picture to look at. But we made some adjustments, like the reaction occurred for a lot longer so that we could get the entire reaction in there. So it's possible, again, that the code was just sort of overwhelmed by all the information. Yes, Sam?
The simulation is producing your nitrous acid, right?
Yes.
Okay. Does it account for like the equilibrium of like forward and backwards, like the creation? Like, does the MATLAB code like count?
Oh. That's a good question.
Feedback reaction?
Yeah, like the equilibrium.
Yeah.
Forward and backward reactions, does it account for?
That's a great question.
Yeah, it is a great question.
And you can just repeat answer to Fred, to Sam. I think that is your answer to Fred will serve as a reasonable answer to Sam. Just explain about probability distribution in both reactant and product regions.
Oh, okay. I think I know what you're talking about. So, okay. Well, in this picture, also part of why there's so much activity going on the bottom here is that's again where the sort of blue canyon that I had. So it's much more likely for the species to be in that area. And that is much closer to the product. So I'm assuming that most of what we're looking at is just the reaction proceeding forward.
Okay. Accepted? Yeah. Okay.
Sufficient. Was that correct?
Okay. Could this go to your potential?
Oh boy. This one?
Yes. So it looks like you are using a MOS potential, right? Instead of a combined oscillator, right?
Why are we using? No.
So this is still a harmonic oscillator.
This is a harmonic oscillator. What? Still no? Oh, still no.
Okay, then good for energy.
With the eigenstates?
Yes, right here. So this is the equation for harmonic oscillator.
Yes.
You try to use different kind of potential, then there should be a correction, right? Then
I'm supporting Dr. Han. It's my major critical point to both your paper and your presentation. Like, what is the reason to show the eigenstates for harmonic two-dimensional harmonic oscillator if your potential is very non-harmonic? Sorry for toasting you a little bit, but If I insist to keep this equation, or you are free to remove it.
If you want me to remove it completely, I can remove it completely.
What was the reason to put it originally?
The reason to put it originally?
The reason why this equation was here, and now you agree to remove it, which makes me happy. But why did you put it here in the first place?
Just I mean, I would guess I wanted somehow to be able to track how the reference point. Oh, yeah. So this equation is used as a reference point.
Okay. And your actual results differ from this reference point substantially.
Yes.
So maybe it's even not a good as a reference point.
Oh, because it's too far from what the simulation actually produced.
Your potentials were imported from what Braden and Sibel did in the past.
Yeah.
So it's extracted from ab initio. So it's very customized potential, and it's not expected to follow these things.
Okay.
And now turn to Dr. Khan and check if he is satisfied with the answer.
Okay.
Yes.
So did you say anything about the rate of this reaction? In other words, in your simulation, is there anything that comes out of it that's analogous to a kinetic barrier for this reaction? And if so, what is the predicted breakdown?
A kinetic barrier. I mean, I don't know if this really answers your question, but this also might not be true at all. Okay, I guess just the first thing that comes to mind with limited thought of it is that, again, since it's more likely that it would exist in this area, this seems like it's fairly easy for the species or the reaction to occur in that spot. So I would imagine if there were a barrier, it wouldn't necessarily be in that area. So maybe it was more at the beginning. So if it's harder for the reaction to occur, I guess initially, and then once it kind of starts, it sort of goes downhill in the sense of the energy that it needs. So maybe there's some sort of activation barrier at the beginning of the reaction, or to even get like the species in the right region to get the nitric oxide sort of formation wise in the right area that it needs to be to interact at all with the iron in the heme B.
Let's cooperate in this brainstorming session.
Okay.
Can you go to your longest movie?
Yes.
And like if the course would be a year long rather than semester long,
this won't really help much, but
which mathematical procedures would you do with your probability distribution to convert it into the rate of reaction that Professor Rogers asked? I hope I'm trying to help, not to make situation worse. Which mathematical procedure would you do to this probability distribution to convert it into the rate of reaction? Do not try to remember anything, just think.
I mean, I understand your question. I don't know.
Can we integrate this distribution in the area of arguments corresponding to the product?
Yeah, sure.
Can we plot it as function of time?
Oh, yeah.
Can we find a slope of it?
Yeah.
And now answer to Professor Rogers and check if you'll be satisfied.
Yeah, so we can kind of integrate the certain section that we're taking a look at. And then I don't know if this is necessarily related to the stuff that I do in lab, but it's similar in the sense that you plot it over time and then you're able to find the rate by taking a look at the slope of the function over time.
Okay, but you don't know what that would be for this simulation.
It would be a little too excessive for the limited.
Yeah, I don't at this time.
Do you know if this reaction occurs in reality?
It does to the limited papers that I've read about it, I think. Or I guess I'm kind of assuming that it would because there's quite a bit of study related to it. But this is not necessarily the main thing that chloride dismutase does. It's just able to also do this.
Does it do it fast? Or does it do it slow?
It does it.
You didn't read our paper on this, did you?
No, I didn't know we had a paper on this. Does it occur slowly?
It's glacially slow.
Okay. Okay. Glacially slowly.
Now, when you know that answer, can you do like reverse engineering and provide explanation why it is going slow? Just maybe looking on the potential.
Oh.
To your two-dimensional this.
Not this.
Potential.
Okay.
Yeah, this one. So can you make a comment if reactant is in the region of higher potential energy and product in the range of higher potential energy?
Oh.
And here the intermediate is much deeper. Can you comment like how would it correlate with the observation that reaction is slow?
So it then to fully get to the product, then it needs another kind of significant boost of energy to be able to fully convert.
Yeah. Based on this potential, it looks like the reaction wants to be trapped in the intermediate.
Yeah.
Whether it is realistic or not, but it how one can interpret the work that Eva is doing.
So just by way of a little context, this reaction is often quite fast.
Okay.
In fact, there are more examples where it's fast than there are where it's slow.
Okay.
The reasons that it's slow in this enzyme and others, a couple of others, probably has nothing to do with the intrinsic properties of the atom system that you're talking about. It has to do with non-bonding interactions that make up the electrostatic landscape of the place where the iron is.
Okay.
Which you're not modeling.
No.
So it's more similar to what Frederick was doing.
I'm sorry, I came in right at the end of Frederick's side.
The reaction by modifying environment and changing the constant of the environment.
Just say yes, Fred.
Yeah. But hemoglobin, for example, does this like a shot.
Okay.
Very inspiring.
Yeah, now I got to do my homework that I should have done before this and read our paper about it.
What does this enzyme actually do?
Oh boy, I have that written in my actual paper, and I spent a while just focusing on that because I didn't really know I was taking a look at this. But I don't even talk about that in the paper. I must have taken that up. Well, it's chloride dismutase. So what was it? It's like ClO2, or ClO. I'm trying to just remember on what I looked at a few weeks ago. And then it ends up producing chloride and molecular oxygen. Is that correct?
The second half is correct.
Oh.
Chloride is ClO2 minus. Right?
Yes, yep.
Hi, good morning, everyone. I'll be giving a presentation on two-coupled oscillator as a model for IR polaritons. IR polaritons also can be known as vibrational polaritons, so I'll be using that interchangeably within the course of the presentation. My presentation is going to go through this outline from introduction through the application. So what is polariton? What is a vibrational polariton? A vibrational polariton is formed when you coupled the vibration of a molecule with the electromagnetic modes of an optical cavity. And when you couple this, when you couple the interaction between the photon and the phonon produces an hybrid state called a polariton, which has a characteristic features of both light and matter. The motion of an IR of vibrational polaritons can be described as a superposition of the normal modes being observed in simple harmonic coupled oscillator. So this is a pictorial illustration showing how a polariton is being formed, where we have on the left the potential energy diagram of the anharmonic oscillation, anharmonic potential of the molecule. And on the right, we have the potential of the cavity, which is anharmonic. And when both interact, they form an hybrid state called the polaritons. From these polaritons, you'll be able to notice when the hybrid states are formed, we notice a splitting between the hybrid states, which is also known as the Rabi energy. The interaction between the photon and the phonon of this system produces three major effects, which are the Rabi splitting, which is also known as the Rabi energy, a change in equilibrium positions, and also energy transitions from the molecular field to the field oscillations, which will be described much later. The Hamiltonian of the system was given by de Pauli, Fraser, and Montonier because it looks a bit too much to take in. So it is simplified into this. Area with the Hamiltonian having the addition of all this, the molecule, the field, and the interactions, where the Hamiltonian, the equation of the Hamiltonian is listed below. The potential for this system is given for the Morse potential. For my stimulation, I was modeling a molecule, and the Morse potential for the molecule is given by this equation, and for the cavity is modeling an harmonic potential, which is given by this equation. The X and the X naught are the equilibrium positions, the initial equilibrium positions of the system before coupling. The parameters for the simulations are thus below. It is very interesting to note that the parameters of the harmonic equation has a relationship to the oscillation frequencies of the systems, where you can see this is oscillation frequencies of the system, which is quite interesting. To fully understand what is going on in a polariton, I decided to model my simulations using MATLAB based on the dynamic and static properties, static analysis of the system. So this diagram or this illustration shows the static properties of an eigenstate. So this is the eigenfunctions of my system this is the eigenfunctions of my systems before coupling occurs. At a certain equilibrium position, you would notice that the center of the eigenfunctions is at the equilibrium positions of the two systems being considered, which is at 3.0 and 0. The middle of the eigenfunction is at there before coupling. And the energy of the system is given by the famous Schrodinger time-independent equations to give the energy of the systems and the wave function, the expectation value of the system. After coupling, we noticed that the middle of the wave function shifted from the previous equilibrium position to a new position here. We could see that the equilibrium position is no longer here, but I shifted somewhere a little bit here for the system, for both this. And this shows one of the observables that we expected to see from coupling for our formation of polaritons, which involves the change of equilibrium positions of the system. This is put in form of change in equilibrium bond length in the molecule and also change the equilibrium strength of the electric fields. I also tried to see how the variation of coupling constants affects the eigen energy states of a system, of a coupled system. So it is interesting to see that when the system was not coupled, we saw that the eigenstate second and third has the difference between the eigenstate and second has a zero. It's equals to zero from here, equals to zero. And that kind of makes sense in a way that because it feels that there's no oscillations, that means the oscillation is zero. So it kind of makes sense based on this equation. So focusing on the dynamic part of my polaritons, this is a video showing the dynamic analysis of the polaritons. From these polaritons, we'll be able to, the dynamics of these polaritons, the dynamics of this wave, eigenwave functions was propagated using the evolution operator. When the evolution operator acts on the wave function, we are able to determine the eigenfunctions of the system at a specific point in time, at any point in time. And if we're able to get the eigenfunctions of a system at any point in time, we can be able to calculate the average trajectory of the system, which this is actually doing at any point in time, in which the molecule of what I'm modeling for my MATLAB code is for a molecule and the electric fields. So we'll be able to measure the equilibrium positions of the molecule and the electric fields. So in this dynamics also, we also notice that as the wave function is moving, in the dynamics, we also notice that there is a transfer of energy from one system to another, from a photon to phonon transfer of energy. As the energy is being transferred from one system to other, we also noticed that there was a change in amplitude of oscillations. As the energy is being transferred, the amplitude of oscillations also decreases with time. And this is shown by this illustration where the maximum of one wave function, the maximum of one wave function is the minimum of another. So we asked ourselves, why do we need to study polaritons? Why is it necessary? So it is said that the polar energy conversion from the molecular bond oscillations to the electromagnetic field amplitude serves as the foundations for the design of a chemical lasers. And also the energy conversion contributes to the field of polariton chemistry to manipulate chemical reactions. So thank you for listening.
Our presentation is open for discussion, for questions.
Yes, please.
In your equations, specifically for the Pauli-Fierz Hamiltonian and interaction Hamiltonian, in one you use chi and in one you use lambda. What is the difference between chi and lambda? And to be fair, it does look like you're doing it on the screen as well, but I was looking at it.
This is the lambda?
That's lambda.
Where's the chi?
Chi would be up at the top.
Right next to the square root 2.
Yes.
I got it. Far right.
Right. This?
Oh, wow. One more.
Left of that.
The X.
Oh, sorry. Here. Sorry. It's the same thing. That was, yeah, that's the, this is actually a constant. Why? This actually represents the coupling strength. So that is actually what I can see because I observed it, but this is a constant. Why? Majorly, to me, I feel it's majorly saying the same thing.
So they can be in different units, but they represent the same concept.
Yes, they represent the same concepts of the coupling strength. Yes.
So other questions from online audience, because we do have experts in the field. So Braden, would you like to ask questions to Patricia?
I'm okay. It was a nice talk. Thank you.
Okay. Yeah. Thank you. Thank you for the evaluation.
So welcome to my presentation. It's on the photo dissociation of 2,4,6-trimethyl benzoyl diphenyl phosphonate. Refer to it as that for the remainder of this presentation. So to start with, I would like to focus in on photoinitiators and kind of the reasoning behind this project. So photoinitiators are compounds that create reactive species upon exposure to light, whether that be UV or visible. There are two categories. It could be either cationic or free radical. In this study, TPOL is a free radical photoinitiator. So when it is exposed to UV light, it cleaves at this bond right here, at this phosphorus carbon bond. So photoinitiators are useful for a variety of different applications, notably in dentistry, in the adhesives industry, and in my area of interest, which is additive manufacturing, also known as 3D printing. So in this project, we're interested in seeing how the behavior of this photoinitiator would change when you vary the intensity of the light that it is exposed to. Okay. So to get into the methods that I used, we had two concepts that were modeled. So we start off with the laser intensity, which we used Rabi cycles. And so a Rabi cycle is the phenomena that is observed when you have a two-level quantum system and it has cyclic behavior in an oscillatory driving field. So basically, and I'll show this in a video later, as the Rabi cycle progresses, you have the probability density just kind of switches from ground state to excited state, which in this project there are a couple of different excited states that were explored. And then the other component was exploring the photo dissociation into the two radicals, which were modeled using a wave packet method. So these are the equations that I mainly focused on. We have the main electron nuclear wave function, which you have all of the different states, 0 representing the ground state, and 1, 2, and 3 are the first 3 excited states. And then we have the partial nuclear wave functions, which are all of these right here. And then once it exhibits the pi pulse, it switches from x up to x down. And then before photoexcitation, when it's in the ground state, all of these probability densities are 0 because there's no excitation that's occurring. And so we have this equation right here. So moving on to the other important equations, we use the time-independent wave function for the probability density, which is the summation of all of the probability densities for the individual states. And so this is the probability densities broken down into their individual equations. So moving on to the results, this is the main chart of the dissociation. So basically, I changed the number of time points in the experiment, as well as the number of Rabi cycles. So we have 4 points for 100, using 1, 2, 5, and 10 Rabi cycles, 3 for 200 using 1, 2, and 5 Rabi cycles, and then 2 for 500 using 1 and 2. I use these specific numbers because after the max number of Rabi cycles, it kind of devolved into chaos in the simulation, and the results basically hit the barrier and became unusable after that. So this 10, 5, and 2 was the last number of Rabi cycles that I was able to implement before it hit that wall. And so looking at this graph, as the number of time points increases, you can see that it starts increasing in the probability of dissociation. So for 100 time points, it took all the way up to 10 before you have any noticeable amount of dissociation, versus for 200, it took 3 cycles, and in 500, it starts in the first cycle and then is complete in the second cycle. And so you can also see a sort of similar behavior in this chart, which is the chart of the bond lengths as time goes on. So you can see, again, it takes 10 cycles before you see any noticeable difference, 5 and 2. So according to these results, when you have more exposure time, and you have a higher power laser, which is modeled by the number of Rabi cycles, then you have a higher degree of dissociation in the photoinitiator molecules. So moving on, so this is kind of a preparation slide to explain the video that is in the next slide. So there's a lot going on this graph. It models the potential energy surfaces as well as the probability density distributions. So these lines, 1, 3, 5, and 7, don't change in the video as time goes on, but you can see as the number of cycles increases, the probability density distributions, so these humps right here, will change. And so we'll watch that video here. So you can see these are moving along as the excitation is occurring. The excited states are becoming populated. And that's all that I have. Questions?
The presentation is open for discussion and questions.
Brett?
So in your movie, just to clarify, when it's like jumping from one, that's like changing between excited states.
So that is that's the implementation of the Rabi cycle. Okay. And so this video is actually specific to I don't remember if it's C or if it's G, but I know it's 5 cycles, and you can kind of tell when it switches to the next cycle based on when it's jumping. And so you can kind of count how many cycles are there. More questions?
So the parameter which you call number of points within one Rabi cycle, which experimental condition does it correspond to? How would one convert it into, like, if you have a expensive system to do laser experiment or just to stimulate it, what the number of points in one Rabi cycle would correspond to?
So from my understanding, that was the time. So in an actual physical experiment, I would translate that to pulses, or like a duration of light on the molecules.
Okay, if we speak in the language of Rabi frequency, inverse of Rabi frequency is Rabi period. So how the duration between flicks of the electronic state relates to Rabi period?
I read about this. Okay, yes, they're equal.
Excellent, excellent answer. Which of your numerical experiments from like A to I communicate larger amount of energy stores larger amount of energy into the molecule? I'm just curious. Even if your answer's wrong, I will be not able to figure it out.
I would say probably I, just because like in this test, it's gone all the way 100%.
Okay, so it secures 100% dissociation.
Yeah.
Okay. And which of the parameters would create the best, most pronounced Schrodinger cat state?
Can you restate the question? Which what?
Schrodinger cat?
Yes, yes.
Which of your initial conditions promote formation of Schrodinger cat? Explain why here and there you have superposition of two different peaks, and in others you don't.
Hold on, let me look through my speaker notes. Okay, so I know the superposition is the bond length. I don't know for sure exactly what is the cause of it.
Why this strand separates, bifurcates on two threads? Why one part goes to the left of the dashed line, another to the right? Just any comments? It's not an exam question. Why here dashed line and the stripe go together, and here they go into the opposite directions?
Well, I mean, as I'm thinking of it now, it could be because it creates two free radicals. It has two kind of opportunities to go somewhere. So it could be it continues on as a radical and initiates other reactions, like a polymerization reaction, or it goes and reforms the initial molecule.
Okay. Can you say that your sample coexists in several electronic states, and then each of which have different potential energy surface and wave packets move with different speed?
I would say that it has population in multiple energy states based off of the video. These humps right here show that there's probability density within each of these excited states.
Okay, Let's count down from check if there are more questions.
Oh, sir.
Those two questions were admiration of the talks rather than the questions. And then I answered thank you to the person who needed to go to the next meeting. Just point. Yeah, but thank you for being on that. So, any more questions to Melody? More questions 1, more questions 2, more questions 3. Let's thank Melody. Special thank you to all participants of this class, the visitors, evaluators, and helpers with the data. Thank you all for investing
the microphone.
This journey. I wish you great success in the rest of the finals and your use. And Merry Christmas and Happy New Year.
Merry Christmas, Happy New Year.
Happy all the other holidays. The last meeting is done.
Yes, let's stop sharing and put this on the.
It's the front. Oh, I don't actually know. Oh, it's right there.
Okay, meeting is done.
Guys.